We are going to look at an important application of Poisson distribution. We are going to call it Poisson approximation to binomial distribution. Before I describe what the application is, I'm going to evaluate the following limit. The limit as n goes to infinity of 1 minus lambda over n to the power n minus k. We are going to use this limit later in the video. So in order to compute this limit, the first thing I'm going to do is I'm going to let u be equal to 1 minus lambda over n to the power n minus k, and we will take the natural log of both sides. So when I take the log of the right hand side, I'm going to get ln of 1 minus lambda over n to the n minus k. Since we're going to use one of the properties of the logarithm to write the right hand side as n minus k times ln of 1 minus lambda over n. Further, we will write this as ln of 1 minus lambda over n divided by 1 over n minus k. Okay, so now we take the limit as n goes to infinity. Remember, we have to find the limit of u, but I'm going to first find the limit of ln of u, which will be the limit as n goes to infinity of ln of 1 minus lambda over n divided by 1 over n minus k. Now notice that as n goes to infinity, the limit of the denominator is this denominator is 0, and also as n goes to infinity, the limit of the numerator ln of 1 minus lambda over n is also 0. So we can apply the L'Hopital's rule, which means that we have to take the derivatives of the numerator and the denominator. So let's do that. Let's find the derivative with respect to n of ln of 1 plus, sorry, I think it is 1 minus lambda over n. Well, this is equal to 1. Let's write it here. This is equal to the derivative with respect to n. Sorry, let's just write the following. This is equal to the derivative of ln of x is 1 over x, so this will be 1 over 1 minus lambda over n, and then multiplied by the derivative of 1 minus lambda over n, and the derivative of 1 minus lambda over n is the following. It is going to be the derivative of 1 is 0, and the derivative of lambda over n is the same as, derivative of negative lambda over n would be lambda over n squared. And the reason I say that is basically you have lambda times minus lambda times n to the negative 1. By the power rule you get negative lambda times negative n to the negative 2 as the derivative, and then you get lambda over n squared. Okay, so now going to do a little bit of algebra here. So this would be actually, let's just keep it the way it is. And now we also need the derivative with respect to n of 1 over n minus k, and again by power rule I can find that this is n minus k to the negative 1. K here is fixed, so this would be equal to minus n minus k to the negative 2, which is minus 1 over n minus k squared. Okay, so let's plug them in. So this would be by the L'Hopital's rule. I can say this is the limit as n goes to infinity, and we obtain the derivative of that is 1 minus lambda over n times lambda over n squared, and here we got negative 1 over n minus k squared, negative 1 over n minus k squared. Okay, so then we have to do some algebra now. So notice what we can write now is the following. Right, let's do the following algebra. So this would be equal to the limit as n goes to infinity 1 over 1 minus lambda over n times lambda over n squared times n minus k squared over negative 1. This would be equal to the limit as n goes to infinity 1 over 1 minus lambda over n lambda over n squared. Let's put the negative here from this negative 1, and I have n minus k squared. So from n minus k squared I'm going to factor out an n, so I get 1 minus k over n, and so I have to square that. This is equal to the limit as n goes to infinity minus 1 over 1 minus lambda over n squared times 1 minus k over n squared. Notice that n squared cancels out, Now as n goes to infinity, lambda over n goes to 0, k over n goes to 0. So what are we left with is negative lambda. Now let me make some room here. Okay, so then what we got so far is that the limit as n goes to infinity of ln of u is negative lambda. But remember, we need to find the limit as n goes to infinity of u, which is the limit as n goes to infinity of e to the ln of u. And since the limit of ln of u is negative lambda, we know that this would be e to the negative lambda. So at the end, remember what u was. U was 1 minus lambda over n to the power n minus k. So at the end, then we could say that this limit, limit here is equal to e to the minus lambda. Okay, so I'm going to pause for a second and then look at how this will be used to discuss the application. Okay, let's now describe the application, that is the Poisson approximation to binomial distribution. So keep in mind that the limit as n goes to infinity of 1 minus lambda over n to the power n minus k is equal to e to the negative lambda. So in order to describe the application, let's consider n Bernoulli trials. So these are independent trials. Each trial results in either a success or a failure. The probability of success is p, and then the probability of failure is 1 minus p. Define x to be the number of successes in n trials. Then we know that x is a binomial random variable. It has binomial distribution with parameters n and p, and so the PMF or the probability mass function of x is given by this equation here. So probability that x is k is n choose k, p to the k, 1 minus p to the n minus k. The possible values of k here are 0, 1, 2, up to n. Now, let's start with the PMF and see how we can obtain the PMF of the Poisson distribution as a limit of the PMF of the binomial distribution. So this is the PMF of the binomial distribution. What I did is I wrote n choose k in terms of the factorials. Now this is equal to, what I am going to do now is express n factorial as n times n minus 1 times n minus 2 times n minus k. So at some point I'm going to get n minus k, and also the numbers below n minus k. So basically I'm going to get n minus k factorial here. So that divided by k factorial times n minus k factorial, p to the k 1 minus p to the n minus k. Now let's cancel out n minus k factorial, n minus k factorial. But we have to realize the factor, the previous factor to n minus k factorial. So this would be n times n minus 1 times n minus 2 dot 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 times the number before n minus k would be n minus k, 1 more than n minus k, so it will be n minus k plus 1 divided by k factorial times p to the k times 1 minus p to the n minus k. Now at this point what I'm going to do is take lambda to be n times p, which then means that we can write p as lambda over n. So let's plug that in our expression of the PMF. So I'm going to write n minus 1, n minus 2 dot 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 n minus k plus 1 k factorial. So p would be lambda divided by n to the k, 1 minus lambda over n to the n minus k. Okay, so next we will say that we will do the following. We're going to write n times n minus 1 times n minus 2 dot 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 n minus k plus 1 divided by k factorial lambda to the k over n to the k times 1 minus lambda to the n minus k. At this point I'm going to switch the order of k factorial and n to the k in the denominator. So I'm going to write k factorial here and n to the k here. Now in the numerator of this fraction I have k factors, and in the denominator I have k factors of n. So what I'm going to do is the following. I can write this as n divided by n times n minus 1 divided by n times n minus 2 divided by n dot 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 n minus, now n minus k plus 1 can be written as n minus k minus 1 divided by n. We have lambda to the k factorial 1 minus lambda over n to the n minus k. Now what we have then is n over n is 1 times n minus 1 over n can be written as n over n, which is 1 minus 1 over n. N minus 2 over n can be written as n over n, which is 1 minus 2 over n dot dot dot. Same way 1 minus k minus 1 over n lambda to the k over k factorial 1 minus lambda over n to the n minus k. Okay, so now we are going to take the limit as n goes to infinity. So remember, we started with the probability that x is k, and we got, that's the PMF of the binomial distribution. So if I take the limit as n goes to infinity of n choose k times p to the k times 1 minus p to the n minus k. Remember, we rewrote this quantity as this. So this is going to be equal to, well, what's the limit of this factor? The limit of this factor is 1 minus 1 over n goes to 0, so the limit of this, the factor in parentheses, is 1. The limit of this factor is 1. The limit of this factor is 1 since k is fixed. This one does not depend on n, so it remains the same. So we get 1 times 1 times 1 times dot 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 1 times lambda to the k over k factorial. And the last thing here, we computed the limit of that, and the limit of that, remember, turned out to be e to the negative lambda. So I get e to the negative lambda. So then finally what we have is that the limit as n goes to infinity of the PMF of the binomial distribution is equal to e to the negative lambda to the k over k factorial which is the PMF of the Poisson distribution.